My name is Jesse Lopez, and this is my protocol presentation video. So first off, we need to establish what exactly is TCP. TCP is Transmission Control Protocol, and that is the protocol that I have chosen to explain to you all today. So the first little bullet point that I have is standard for exchanging data between different devices in a computer network. So when you connect to the internet, you establish a connection between a router and a computer or a mobile device in a few steps, whether you're on wireless or wired. Nothing else is really required because the system automatically logs into the network and obtains a unique internet address that you need to receive and send data. This is made possible by a set of protocols known as the IP suite or the Internet Protocol Suite. One of the oldest and most important protocols is TCP. It determines how network devices exchange data. So TCP is Transmission Control Protocol, and it is a standard for exchanging data between different devices in a computer network. This protocol dates all the way back to 1973, when computer scientists Robert E. Kahn and Vinton G. Cerf published the first version of the standard as part of a research paper. It took another 8 years before TCP was standardized in RFC 793, though. Since then, there have been a number of improvements and extensions, although the core of the protocol has remained unchanged. The current version, which is defined in RFC 7323, is from 2014. The current version of the TCP protocol allows two endpoints in a shared computer network to establish a connection that enables a two-way transmission of data. Any data loss is detected and automatically corrected, which is why TCP is also called a reliable protocol. Together with UDP, server know-how, UDP user diagram protocol, and SCTP, TCP forms the group of transmission protocols belonging to the Internet Protocol Suite that are located at the transport layer in the network architecture according to the OSI model. The term TCP/IP protocol stack is also commonly used to refer to the Internet Protocol Suite, since the TCP protocol is almost always based on the Internet Protocol, and this connection is the foundation of the majority of public and local networks and network services. So how exactly does TCP connections work? TCP allows for transmission of information in both directions. This means that the computer systems that communicate over TCP can send and receive data at the same time, similar to a telephone conversation that you'd have with your friend or coworker. The protocol uses segments as basic units, also called packages, of data transmission. In addition, the payload segments can also contain control information and are limited to 1500 bytes, 1500 bytes. The TCP software in the network protocol stack of the operating system is responsible for establishing and terminating the end-to-end connections as well as transferring data. The TCP software is controlled by the various network applications such as web browsers or servers via specific interfaces. Each connection must always be identified by two clearly defined endpoints, client and server. It doesn't matter which side assumes the client role and which assumes the server role. All that matters is the TCP software is provided with a unique ordered pair consisting of IP addresses and port, also referred to as tuple or socket for each endpoint. So how is a TCP connection established? That is through the three-way handshake. What is a three-way handshake, you ask? To have a three-way handshake, you must have a unique IP address. So the prerequisites for establishing a valid TCP connection, both endpoints must already have a unique IP address and have assigned and enabled the desired port. for data transfer. The IP address serves as an identifier, whereas the port allows the operating system to assign connections to the specific client and server applications. So the actual process broken down is the first step is the requesting client sends the server a SYN packet or a segment. SYN stands for synchronize with a unique random number. This number ensures full transmission in the correct order without duplicates. Second, if the server has received a segment, it agrees to the connection by returning a SYN ACK packet. ACK stands for acknowledgement, including the client sequence number +1. It also transmits its own sequence number to the client. Finally, the client acknowledges the receipt of the SYN ACK segment by sending its own ACK. So almost a SYN ACK, but they don't really call it that, which in this case contains the server sequence number +1. At the same time, the client can already begin transferring data to the server. So while all this is happening, it connects and it acknowledges, but it also starts to send the data after it acknowledges it. So the teardown of how a controlled TCP connection termination works. Both sides of a connection can terminate a TCP connection, and even one-sided termination is also possible. That is known as the half-open connection, whereby the other side is still allowed to transfer data, even if one side has already disconnected. So the breakdown of the two-way termination, which is initiated by the client for the sake of simplicity in this example, can be summarized as follows. Number one, the client sends an FIN segment to notify the server that it no longer wants to send data. It sends its own sequence number just as does when the connection is established. The server acknowledges the receipt of the package with an ACK segment that contains the sequence number +1. When the server has finished the data transfer, it also sends a FIN packet to which adds its sequence number. Now it is the client's turn to send the ACK packet, including the sequence number +1, which officially terminates the TCP connection for the server. So back to this, however, the connection is not immediately terminated for the side that sent the last ACK segment. Since there is no guarantee that the last packet sent has actually arrived, the client or server will initially remain in the time wait state until the maximum lifetimes of the ACK segment and any new FIN segments, according to FRC 793, 2 minutes for each segment have expired. So the TCP header. What is the structure of the TCP header? I have bullet points, but I can explain those in further detail. So the header of a TCP packet contains the data required for connection and data transmission with the transmission control protocol. This header data, which contains control information, precedes the payload to be transferred and is typically 20 bytes, 160 bytes in size. It is followed by 40 bytes of additional information, which is optional and not used in all packets. So the source port identifies the port number of the sender. The destination port identifies the port number of the receiver. The sequence number specifies the first byte of attached payload data or is sent when the connection is established or terminated. It also used for validating and sorting these segments after transmission. The acknowledgement number, this field contains the next sequence number that the sender is expecting, an ACK flag. The offset field specifies the length of the TCP header in 32-bit words to highlight the starting point of the payload data. This starting point varies from segment to segment due to the variable options. Reserved for future use according to RFC 793 and not yet in use. This field must always be set to 0. Flags. There are 6 possible flags, single bits in the flags. Field enable various TCP actions for organizing communication. URG, the urgent flag, ACK in combination with acknowledgement number. PSH, the push flag, ensures that a TCP segment is immediately pushed through. RST, if there is not an error, a TCP packet with the RST flag can be used to reset the connection. SYN, messages that have SYN set represent the first step of the three-way handshake, meaning they initiate the connection, and the FIN, or the finish flag, sends the other party that is sender ending the transmission. Window size, this field specifies the number of bytes that the sender is willing to receive. A checksum is a transmission control protocol that can reliably detect transmission errors. It is calculated from the header, the payload data, and the pseudo header is used for this purpose. The urgent pointer indicates the position of the first byte after the payload data is to be processed urgently. As a result, this field is only valid and relevant in the URG flag is set. And then the options, use the options field if you want to include TCP functions that don't belong in the general header. For example, if you want to define the maximum segment size, the length of the options must always be set to a multiple of 32, otherwise 0-bit padding is required. So a quick summary of what we just went over. TCP is a connection-oriented, enables two-way communication between two endpoints after the three-way handshake. TCP is reliable because the protocol ensures that all data is fully transmitted and can be assembled by the receiver in the correct order. TCP always allows data to be sent in individual segments up to 1500 bytes in size. TCP is positioned at the transport layer, layer 4 of the OSI model. TCP is usually used in conjunction with the IP and is commonly known as a TCP/IP protocol stack. The TCP header has a default size of 20 bytes. Up to 40 bytes of additional options can be added though. So that was a quick rundown of the internet protocol. Hope you enjoyed it. Have a wonderful day.